Hello everyone, welcome back to Chemical Engineering and Aspen channel. In our today's video, we will again do manual calculations of an equipment and then compare the results with the Aspen as we have been doing the same task in our previous two videos. Previously, we selected distillation column and heat exchanger, and today we will be selecting the reactor module or the reactor equipment to perform this task. By first we will do the calculations manually or handwritten calculations, and then we will use Aspen simulation, finally comparing both the results. So if you have not subscribed to the channel yet, please subscribe to the channel. Click on the bell icon to get all updates related to this channel. So going to the problem statement is that ammonia is burned to produce nitric oxide. The fractional conversion of the limiting reactant is 0.5. The inlet molar flow rates of ammonia and oxygen are 5 mole per hour each. The operating temperature and pressure conditions are 25 degrees centigrade and 180 respectively. Calculate the exit components molar flow rates assuming reactor operates adiabatically. This is the flow diagram that 5 mole per hour of ammonia and 5 mole per hour of oxygen at a temperature of 25 degrees centigrade, pressure of 1 atm are fed to this conversion reactor, or in Aspen Plus language we can say it as stoichiometric reactor, where this reaction takes place that can be said as 4 moles of ammonia reacts with 5 moles of oxygen to produce 4 moles of nitric oxide and 6 moles of water. And in the product, we get unreacted ammonia, unreacted oxygen, produce NO, and produced water. So we will now move to the solution part, and there are two types of solution that are available. Number one is based on the extent of reaction, and number two is based on creating the stoichiometric table. So coming to the solution number one, which is based on using extent of reaction, we know the stoichiometric coefficient. For ammonia it is -4 because for reactants we say minus, and for products we say plus. For oxygen -5, for NO 4, and for water it is 6. Now the extent of reaction method can be used to calculate the outlet molar flow rates. How it can be written: N of I, which is the number of moles of species I, is equal to, or that can be said at the outlet of the reactor, is equal to number of moles of species I at the inlet of the reactor plus the stoichiometric coefficient multiplied by the extent of reaction. For ammonia, it is N of NH3 at the outlet of the reactor is equal to N naught NH3 minus 4 into extent of reaction. Similarly, for oxygen, NO2 is equal to NO2 initial, which is presented as naught minus 5 into extent of reaction. For NO, plus 4 into extent of reaction, and for water plus 6 of extent of reaction, while the initial flow rates and the final flow rates are mentioned over here. Now the total number of moles at the outlet of the reactor can be calculated. Obviously we will sum all these: -4, -5, +4, +6 to get the final expression as N is equal to N naught plus extent of reaction. So now the inlet molar feed flow rates for ammonia is 5 kmol per hour. For oxygen, it is 5 kmol per hour. NO is 0 and water is also 0 at the initial conditions. Now we are assuming the limiting reactant as oxygen. So accordingly, the fractional conversion can be calculated as X is equal to NO2 at start at the inlet of the reactor minus at the outlet of the reactor divided by at the inlet of the reactor. Accordingly, X is given as 0.5 because we have been given that the fraction of the limiting reactant is 0.5. Inlet flow rate is 5. Again, it is 5. So we will calculate NO2, which is 2.5. So the molar flow rate of oxygen at the outlet of the reactor is 2.5 kmol per hour. Now substituting this value in the previous equation, which was NO2 is equal to NO2 naught minus 5 epsilon. Now NO2 is 2.5, NO2 and initial condition is 5 minus 5 times epsilon. So the epsilon answer or the extent of reaction answer will be 0.5. Now accordingly, we will put the value of 0.5 in all these expressions, this one, this one, this one, to get the answer as N of ammonia 3 kmol per hour. Oxygen it is calculated already as 2.5 kmol per hour. For NO it is 2 kmol per hour, and for water it is 3 kmol per hour. So this is the first method to calculate the outlet molar flow rates, and this method uses extent of reaction method. Going to the solution number 2, we will create a stoichiometric table using the Fogler theory concepts, and then we will proceed further. So we have described oxygen as A because it is limiting reactant, ammonia as B, NO as C, water as D. Now the initial molar flow rate for obviously species is Fa0, for B Fp0, Fc0, and Fd0. Now that Fc0 and Fd0 are 0 because there is no molar flow rate of NO and water at the start of the reaction or at the inlet of the reactor. Now the change will be minus Fa0x minus B over A Fa0x plus C over A Fa0x and plus D over A Fa0x. Remember that the equation will be adjusted in such a way that the stoichiometric coefficient of the oxygen will be 1, or you can say minus 1, and accordingly it will be adjusted. So this now sums up as Fa is equal to Fa0 minus Fa0x or Fa0 into 1 minus x. This will be F of B is equal to Fp0 minus B over A into Fa0x. F of C is equal to Fc0 plus C over A Fa0x, and F of D is equal to Fd0 plus D over A Fa0x. And obviously you can sum all of these and then you can do some calculations, but that are not part of our today's lecture. And coming to the manual calculations, now Fa is equal to Fa0 minus Fa0x, Fa0 into 1 minus x. Now the inlet molar flow rate of oxygen is 5, conversion is 0.5, so accordingly we get the molar flow rate of oxygen at the outlet of the reactor as 2.5 kmol per hour. For ammonia, Fb0 minus B over A Fa0x, Fb0 is 5, B small b is 4, A is 5, Fa0 is 5, X is 0.5, accordingly we get the answer of 3 kmol per hour. Fc0 plus C over A Fa0x, 0 plus 4 by 5 into 5 into 0.5, answer is 2, and similarly for water it is 3. So now you can see these answers are the same as we have calculated from the solution number 1. Now we will go to the Aspen Plus, we will add the components, add the property package, and we will use the stoichiometric reactor to simulate the process. So we will now come to the component selection part. First one is ammonia, then oxygen, NO, and water. Clicking on next, and we will select the property package as Peng Robinson, and then clicking on the run button, and results are available. We will now go to the simulation environment and we will select the stoichiometric reactor. Going to the reactors, this is RSTOIC, which is the stoichiometric reactor. Then we will do the connections, inlet and outlet connections. Then we will specify the feed, which is S1, so that is 25 degrees centigrade, 1 atm, molar flow rate of ammonia as 5 and oxygen as 5. So the feed is specified. Now going to the reactor, 25 degrees centigrade, 1 atm, the same condition as that of the feed. Then we will add the reaction, clicking on this new. Ammonia and oxygen are reactants, NO and water products. -4 for ammonia, -5 for oxygen because minus represents that these are the reactants. 4 for NO and 6 for water. Fractional conversion is 0.5 for oxygen. Clicking on this next button and now clicking on this run button, and we will get our required results which are now available. So going to the stream results, and in stream results we can see that the molar flow rate of ammonia at the outlet of the reactor is 3, oxygen 2.5, NO2, and water as 3. So this is our second part of today's simulation. Going to the third part, that was the comparison. So if you see that if I take you back to the slides, that the molar flow rate of ammonia was 3, oxygen was 2.5, NO was 2, and H2O was 3. So water is 3, NO is 2, oxygen is 2.5, and ammonia is 3. So both results, which are the manual calculations or handwritten calculations, and Aspen results complement each other or they are equal. This was the objective of today's activity, to make you understand that manual calculations are equally important and they play a vital role once we talk about the Aspen calculations as well. So I hope you have understood all the aspects of this lecture. If you have any queries, feedback, suggestion, please provide it in the comment box and I would be happy to answer it. So that's it from today's lecture. Thank you so much. Please do watch, like, share the video and subscribe to the channel. Also click on the bell icon to get all updates related to this channel. Till then, it's goodbye. Stay tuned for more exciting videos on this channel.